let's be aware that there's an awful lot to come. We have to deal with chapters 20 through 23, certainly by the end of term, and I then summarize the later chapters in the book to make sure that you're ready for the biochemistry course. A lot of this is functional group manipulation. A lot of it is functional group chemistry, which we have done, or we have seen things that are related to it. There will be a lot of chemistry from now on. There are at least 30 or 40 mechanisms before the end of term. Many of them are the same. Okay, we can do that in recitation, we can do it in office hours and point out the fact that some of these things are the same, they overlap, so you don't have to learn everything, you just have to understand what's going on so you can compartmentalize things and then understand that the chemistry isn't that difficult. So, talking about here the carbonyl group, the idea that the carbonyl group is something we have talked about already. What shape is a carbonyl? It's planar, it's flat. Okay, that will make a difference in a minute when we start attacking it. We'll have to worry about nomenclature very briefly. A lot of that is up to you because it's pretty straightforward and quite dry, but you do need to understand what these things are called, especially in biochem when these things show up. Aldehydes and ketones, don't forget the aldehyde is the molecule that has an H right there instead of a carbon, and that has its unique NMR properties. You can see a proton signal down at 9 ppm, which you wouldn't see for a ketone. If you have a ketone, you have two carbon groups attached. You have the alpha carbonyl signals in the C13 and in the proton spectrum, and we can differentiate between these two types of groups quite easily. Now, examples of where these things show up in nature, they're everywhere. Okay, they're just ridiculous in terms of their presence in nature. Vanillin, okay, vanilla flavoring. You can see the aldehyde right there on a benzene cycle. It's a tri-substitute to benzene. Cinnamaldehyde certainly is, you know, it smells and tastes like cinnamon. And you can see here a trans double bond coming off a six-membered ring, and then the aldehyde at the end. And we'll start thinking about where the names come from. So aldehyde is an obvious one. It's a dead giveaway. Carvone, the end of the name here, "-one", suggests that it's a ketone. Anybody who's in pharmacy or has worked as a pharmacist or a pharm tech or whatever, you look at the names of pharmaceuticals on a bottle, and you'll often see the functional groups incorporated into that name. Okay, the use of, you know, an ol for an alcohol or an one for a ketone, stuff like that. Benzaldehyde, benzaldehyde is kind of fun because it smells like almonds, but so does cyanide. So you need to be careful which one you're dealing with. And you can see now that we have a whole bunch of common names that have stuck, mainly because of pharmacy and because of natural product chemistry. And we do have some systematic names. So we'll spend a little bit of time talking about how to name these things, and then we'll dive into the chemistry. Chapter 20 is big, and you can't leave chapter 20 until too late. That's why the average goes down. People are worrying about physics or biology or all those easy subjects. You can't leave this stuff alone. You have to keep on it. So in terms of complex molecules that you've probably heard of, and you will certainly see in the future, progesterone and testosterone, okay, hormones involved in differentiation of the sexes. Progesterone is a diketone, whereas the testosterone has the secondary alcohol up here. Basically, not a lot of difference, right? The structure of this thing is very similar to the structure of that thing, and basically the difference is one ketone up here versus one alcohol down there. Yeah, and that has a very, very profound effect on biological processes. Reducing that down to the most simple type of aldehydes and ketones, on the left we have formaldehyde. Where do we see that? Where's that used? Embalming. And acetone over here, where's that used? In the lab to wash your dishes. Yeah? So it's a very useful solvent. So these things are everywhere. And what we need to do very quickly is get over the naming so we can get into the chemistry. This is quite dry and you'll be responsible for it yourselves. And this can be a bit confusing because of the fact that the aldehyde's functional group is a carbon. And when you think about carbon chains and how long they have to be, can you include that carbon in that chain? Right? That will be one of the issues here, why we get so many different types of names. So to start off quite easily, methanal is easy enough. The ending gives it away. Al is an aldehyde. So methanal, one carbon, could also be called formaldehyde. If you went to the shop and you asked for methanal, people wouldn't know what you were talking about, but they know what formaldehyde is. That's the problem with this subject, is there are many different names, some of which are more common than others. Ethanal starts to get into sort of, you know, the organic chemists might call it ethanal. The pharmacists and the biochemists might call it acetaldehyde, but they're both the same. And acet, I think we've seen a little bit before, acetic acid is a 2-carbon piece, which has a carboxylic acid there. And so the acet at the front is a 2-carbon piece, and the aldehyde is obviously the functional group. You need to be aware of both of them, not just for my class, but for the future. Then we get into the less common ones, which aren't so prevalent in biochemistry, and so they tend to have their own sort of name that organic chemists would use, in this case propanal. So what we've done so far is count the longest chain and then call it an aldehyde. That's all you need to do right there. Some other examples that aren't so easy to sort of compartmentalize. Benzaldehyde, this one here, you can't include that carbon in the longest chain, right, because it's a cycle. So the benz obviously is the benzene ring, the aldehyde is the aldehyde component, and that's benzaldehyde. And the ones that I think are particularly awkward are things like this. We have a cyclopentane cycle or a cyclohexane, something like that, and then carbaldehyde. Okay, this is saying that the carbon here is part of an aldehyde functional group, and that gives you the outcome there. Practice it, and you'll get familiar with these things. At the end over here, again, just an example of how an organic chemist might call this thing. E3-phenylpropenal should be something you can disassemble. The al is the aldehyde at the end. The propene is this part here with 3 carbons, and the phenyl group is over there. What does E mean? Trans, exactly. And that commonly is called cinnamaldehyde. Now, in terms of ketones, very similar. For the simple types of molecules, you can keep an eye on the length of the chain, look where the ketone is, and maybe give it a number. Do you have to give an aldehyde a number? Necessarily. It's at the end of a chain. Keep an eye on that. The difference with an aldehyde and a ketone is the aldehyde is at the end of a chain, whereas the ketone is usually inside a chain. So you do have to give it some number to differentiate from where else it could be. So acetone. We can see here 3 carbons. The IUPAC name would be propanone, 3 carbons. Do I need a number here? Do I need a number to tell the reader where that ketone is? No, we do not. Why not? If I put the carbonyl at the end, what does it become? It becomes an aldehyde. Yeah, so that simple system, you can't, you don't need a number right there. What about butanone? Do I need a number? No. If I move the carbonyl to the next carbon along, it's still 2-butanone, and it's still butanone, and if I put it at the end, it's a butanal. So you don't need to worry about that there. When we get to the longer chains, yes, you have to be concerned about where that carbonyl is, and you have to give it a number. So here we can see 2-pentanone. Why? Because if I move the carbonyl from the right into the middle down here, it becomes 3-pentanone. That's an isomer, that's different, you have to say so. Examples down here that you'll see a lot of. We have made this stuff by Friedel-Crafts acylation. We're now using this stuff in class and in recitation to be able to do synthesis. And you can see now methylphenyl ketone is one way of getting around this. Methyl group on the right, phenyl group on the left. It's all about alphabetization. Methylphenyl ketone is obvious, and acetophenone is the common name. You probably want to be aware of both. Here you can see now just a simple system where you're applying the alphabetization of the substituents. One is a cyclopentyl group, one is a methyl group, and so cyclopentyl methyl ketone. You might see a couple of points worth of nomenclature on there, but what I tend to do from now on is include it in a question, include it in a longer question, so that you know the name to be able to do a question such as a mechanism. So be on top of this stuff. Over here, diphenyl ketone should be okay. 2 benzene rings, phenyl groups, diphenyl ketone in the middle. Everybody calls it benzophenone. I blame the pharmacists, as everybody does. All right, so nomenclature is primarily up to you. Give it a go, practice some things, and we should be in good shape. There are some sort of concerns here in terms of the fact that this is a functional group. The ketone and the carbonyl and the aldehyde now are very important functional groups. Okay, they have a high priority. And so if you were looking at a system like this, on the left, our simple alkane, you just use the rules as we've seen them so far. You don't need to be concerned about including a functional group because there isn't one. So this one would be octane, and it would be 1, 2, 3. It would be 4-methyl octane. That's stuff we've done for months now. On the right-hand side, you've got to be careful now because you must try and include the aldehyde in the longest chain. And so in this example, the longest chain is not this along left to right. It is taking a diversion up to here, and it turns out that's a 6-carbon chain. That's a hexanal. So what's the substituent here? That's a propyl group, right? And which carbon is it at? What number would you give it? 2, exactly. So 2-propyl hexanal would get away with that. Again, be careful with numbers. You want to keep your numbers small. This is a high priority group now. The aldehyde here is going to win. And so it gets number 1. It does not get number 7. Just keep the same sort of sensible ideas rolling, and we should be fine in terms of naming stuff. Fair enough? Feels like a Wednesday. Yeah. All right. Now, this is here to sort of wake you up and to recognize, or make you recognize that those of you who get by learn and dump, they learn for an exam, then they forget it all, then they learn something different for another exam, then they forget it all. This isn't going to work because you know a lot of carbonyl chemistry already. So you need to go back and look at these tables from the book, table 20.1, and understand that you've seen this before. We're not going to reteach it. We understand or we recognize that you know what this stuff is about so that we can use it. We've made carbonyls, we've made them by oxidation, we've made them by, let's say, hydration of an alkyne, things like that. This is, quite a ways in the past. But these are important reactions. You can take a primary alcohol and you can use PCC. What was PCC? Pyridinium chlorochromate, right? It's an oxidant. What does it avoid? What does it not go to? The carboxylic acid. It's been a while. I can see people going, yeah, it's been a while. It does not give the carboxylic acid. What was the fundamental idea behind that? What's missing from this reaction mixture that was needed to give the carboxylic acid? Water, exactly. So that's now a nice way of making aldehydes, and you can make ketones too if you'd like. You can also do ozonolysis. This was a ways back. You can take a alkene, and you can cook it up with ozone, and you've got that marvelous mechanism where they attach, they detach, they attached again, and then they got reduced, and you can make 2 carbonyls by that. And that was a lot of fun because you take a cycle, like cyclohexene, and you can open it up to make a chain. So be aware of that type of thing. This one, everybody's favorite from last semester, the parachute borane, the idea of the Lewis acidity of that guy and the steric hindrance in the transition states leading to one regioisomer being preferred over another. This was like the anti-Markovnikov addition of water to an alkene. And if you use an alkyne, for example, here, and then you get the hydration process, that was key. That was a really important step. What was the main feature of that, the hydration process? You get an enol, and then you get to a ketone. What was that step? Tautomerism. So if you don't like tautomerism, unlucky. We're about to do it a lot. And it's a hidden step. It's something you have to be aware of. So make a note of tautomerism and go back and look at it again. Now over on the right-hand side, to make, in this case, we're making ketones. You can take any secondary alcohol usually and oxidize it using any of those reagents. PCC works, PDC, sodium dichromate will all work because you're not concerned about over-oxidation. Once you get to a ketone, that's the end of it. You don't have an extra hydrogen here on the ketone, so you're not going to go any further. We can also do osmolysis again if we have poly-substituted alkenes. We can break them apart to make ketones. And we can do this again with the alkynes. This system here was the opposite of this system down here on the left. This was the Markovnikov addition. We're not using the boron here. We're using Lewis acids, and we're using nucleophilic water, and we're ending up with the Markovnikov addition through the better possible carbocation. So again, we've seen this stuff. It's got to come with you. We have just done this, Friedel-Crafts acylation. Obviously, you can see now the context of the course. We just spent a lot of time on this. We'll be using it. That's a good way to get to a ketone on a benzene system. The Friedel-Crafts reaction is very useful because it gives you a deactivated benzene, which does not go any further. It's a very clean process. So that was 2 minutes on that, right? But we've spent probably a week on that chemistry in the past. Go back and look at it, make sure you understand it. So basically the carbonyl is one of our most important functional groups because it is so useful. You can do so many things with it. You can attack it. You can use it to attack other things. We'll see now that most of the chemistry we will do in this class from now on involves nucleophilic attack on something else. In this case, the carbonyl will be the electrophile. And what I want you to understand from this is the sort of key for this chapter. The way the carbonyl is set up, it's very highly polar. The idea of having that oxygen right there on the carbonyl is obviously pulling electron density towards it. But when you put a pi bond in there, and those pi electrons are weakly held, we find that those electrons are much closer to the oxygen. And so this resonance structure becomes very important. This second resonance structure here is the key. Between those two, don't forget resonance structures are trying to describe what the molecule looks like overall. We could draw this thing in which we put delta positive on the carbon and delta negative on the oxygen. So don't forget also we have lone pairs on O, we don't have any lone pairs on C. But down on carbon now, that reminds you of a carbocation. We'll be doing exactly that. We'll be saying that this carbon acts like a carbocation and this oxygen up here behaves like a base. So if you put a proton in here, where would it go? If you added a proton to this molecule, where would it go? Oxygen. If you added a methyl minus, if you added a nucleophile, where would it go? If you added anything negative, where would it attack? The carbon. That's all there is to it. That's all there is to this chapter. Just many, many examples of it. So there's a little bit of a detail here. You can see at the bottom, one of the typical conversions here will be taking the flat, planar sp2 hybridized carbonyl and turning it into something more elaborate, turning it into a three-dimensional shape where the carbon in the middle is now sp3. So you get a hybridization change as the reaction is progressing. And we'll see now that the reaction isn't straightforward. It isn't just sort of a right-angled attack. It isn't a nucleophile attacking from the top and pushing things away. It's been proven that the angle of attack is about 107 degrees. Okay, and that then lowers the transition state energy because this is closer to 109. It's somewhere in between 90 degrees and 109, and it's giving you the best trajectory to give you the lowest energy transition state as you go from flat on the left to sp3 on the right. But most of what we'll do now is take some nucleophile, add electrons to the carbonyl, and push electrons up onto oxygen. That is nucleophilic addition that we've seen before. We've seen it with Grignards, we've seen it with Hydrides, and now we fill in a bunch of other things. So here we go. We've got to be concerned now about how reactive these things are. There'll be some arguments coming up which are very subtle, but they are related to biochemistry. The idea of hydration, for example. If you put water in the presence of one of these molecules, what does the system look like? Is it an aldehyde or is it something different? Does the water get involved? And this is all related to how stable the different pieces are. So we have an argument here about how stable ketones are versus how stable aldehydes are. And this is fundamental. Again, if you want to put your smiley face on here, your asterisk, your question mark, whatever you do, your thumbprint, this is an important section. Ketones are generally more stable than aldehydes. Okay? Ketones are less reactive than aldehydes. They're both reactive, both much more reactive than, say, carboxylic acids or esters, and we'll compare those later. But in the argument here between these two, the ketone is less reactive and therefore more stable than the aldehyde. And there are arguments here which should be fairly simple. You look at the top picture on the left. A ketone, by definition, contains two alkyl groups of some kind. And those alkyl groups are electron donating. So if you think about the nature of the carbon in the middle, that carbon in the middle of the carbonyl is delta positive. It wants electron density. So if you have alkyl groups attached, they will help that out. They will help stabilize that. It's somewhat similar to having alkyl groups on double bonds. When you think about the Zaitsev rule, you wanted alkyl groups on double bonds so that they helped out the sp2 carbons. This is just a bit further. The alkyl groups really help out because the carbon here is quite positive, and if you have electron donating groups here which can push electrons in, they will help stabilize the ketone. The problem with the aldehyde, you've taken one of those pieces off. Okay? You've taken away one of those carbons, so therefore it can't help. Pierce. We'll do that soon. We will do exactly that soon. All right? Now this is, as you start to think about biochem, because registration will be coming up fairly soon, and most of you will be looking at biochem. Nature is very subtle, very clever, in terms of using very slightly different structures to do very different jobs, and that leads to specificity, right? And leads to selectivity in nature. It's a very difficult thing in the organic lab to be able to differentiate an aldehyde from a ketone. You put most nucleophiles into a mixture of aldehyde and ketone, the nucleophile goes for both of them. There isn't much difference, but there's enough difference in biology with other circumstances involved to be able to differentiate. But right now, if you're looking at rates of reaction, which should go faster, the aldehyde or the ketone? The aldehyde, right? It's less stable to start with. It's also less sterically crowded, if you like. If you take a R group here and this R group on the left starts to get quite large, maybe that carbonyl starts to get a little bit blocked. Whereas on the right-hand side, the aldehyde with the hydrogen, there's no problem there. But then there's a little twist at it as well. Look at this system at the bottom. We're going to see a problem as products are produced in terms of what's called steric compression. So we look at the system here. The two R groups on here could be anything. And that molecule is flat. So typically that is easy to attack. There's no problem attacking that carbonyl because it's flat, just like a carbocation. Now if you start bringing in a third R group here, and you start to attack this thing, you're going to start creating some strain around that central carbon. These R groups here are now getting closer to each other. What was the bond angle here in the left-hand side, in an sp2 hybrid system? 120, right, 120. What's the angle here ideally on the right-hand side? 109. So we're getting closer, right? The pieces are getting closer. And if those things start to get larger, you can get some problems. And that can lead to a destabilization of the product or a destabilization of the transition state leading to it. And again, this is subtle. You have to think about this stuff. But these are some real issues that you'll take with you. So from that slide, aldehydes are more reactive. Ketones are less reactive simply because of electron donating effects that you should be okay with. Now, we'll start this off. I mentioned last week or Monday and the week before spring break, that an understanding of pH is really key here. If you just don't get pH, this won't work. But if you understand the idea of adding acid to something is adding positive pieces, then we can start thinking about mechanisms that involve positive intermediates. And you think about bases being negative things, or at least electron-rich, hydroxide. Then if the hydroxide is negative, the intermediate species tend to be negative. So this slide is setting things up. This is just a generic picture trying to set things up for what's to come, because what will happen next is a whole bunch of examples using O or N or S or carbon to attack that carbonyl. So we have a couple of different environments here. At the top, we have the basic conditions in the flask. At the bottom, we have the acidic conditions in the flask. Very different. Now, at the top, what is the pH? Greater than 7 or less than 7? Greater than 7. We should not have to think about that at this stage of our lives. Okay? It's greater than 7. So how much acid is around? None. No. You don't have any H plus there because it's greater than 7. That's something we should have learned from freshman chem. So what we'll find now is that the types of nucleophiles we will use belong to a certain family. They will be hydride, from lithium aluminium hydride. they will be methyl magnesium bromide, the Grignard reagents, because those are basic reagents that cannot live in the presence of acid, because the acid would protonate them and kill them. So at the top, we have a fundamental process of nucleophilic addition dependent upon the conditions in the flask, dependent upon the pH in the flask, and by extension, the pH in a physiological system. So we're going to see now nucleophiles, some of which we've already done. We did methyl magnesium bromide, phenyl magnesium bromide, and everybody was quite happy with this negative thing attacking this delta positive carbon when we made alcohols in the first chapter of this term. So in this example, you're not protonating anything yet. And in fact, this might be a two-process or a two-step process in which you mix your ketone or aldehyde with the nucleophile in some solvent and let them react. And at the end of the day, you add some water. What's that step called? That's a quench, absolutely, that's a quench. So you've put, if you want to write something down here, you've already done this. Grignards, LAH, sodium borohydride, stuff like that, okay? And we will see more examples of that, where the instability of the nucleophile precludes the use of an acid in that first step. You just can't use it because it will protonate the nucleophile. So that will be a key fundamental mechanism that you will see again and again over the next week for how nucleophiles react with aldehydes or ketones under basic conditions. And you absolutely have to identify whether it's acidic or basic to start off with. That's the first thing you look for. So with that in mind, two steps. Nucleophile in, form alkoxide, which again is a negative species. Look at this, we're under basic conditions with negative species. There's a negative species. And if we deprotonate water, this breaks off as hydroxide. That's a negative species. The entire mechanism features negative species, something that you can get a hold of. At the end of the day, you get your sp3 hybrid alcohol. Now, let's change that. Let's go from highly basic conditions, high pH, to acidic conditions, low pH. And now what we've done here is added acid. We have acid in here to lower the pH. So what's the fastest reaction you're aware of? Acid-base reactions. And if you have a decent acid in here, something strong like HCl or H2SO4, certainly that acid-base reaction should go first. So many of the other mechanisms you'll see now rely upon identifying that. Do I have an acid or do I have a base? In this example, HA is now going to protonate something, in this case the carbonyl. And as we head towards the later chapters, and you have 5 or 6 different places to protonate, you've really got to be on your toes. Because you can protonate in a bunch of different places, but often only one place is productive in terms of going to the product. And we have to understand the thermodynamics behind that and the kinetics behind that, and it gets quite complicated. So here we go. Second idea here, low pH, acid. And you protonate something first. And this now should start to look familiar. We have protonated things in the past to improve their ability to do certain things. If you protonate a hydroxyl group on an alcohol, what's that trying to do? It's trying to make it a better leaving group, yes? If you protonate an OH group, you have more of a chance of that water molecule breaking off than you did of having hydroxide break off. That's fairly simple. Well, what if you protonate this species here? What do you think it does to the reactivity of this molecule? Makes it more reactive or less reactive? It makes it more reactive for similar reasons, right? Think about what happened in that first step, even with an alcohol molecule. How electronegative is O? Highly electronegative, yes? Does it want to share electrons or not? No. If it is forced to share electrons by reacting with a strong acid, it wants them back. So the chemistry after that often is trying to get those electrons back. When you protonate an OH group to make it a leaving group, it breaks off so the oxygen gets its lone pair back. That's exactly what happened, because it's so electronegative. And guess what? What's more electronegative than O? Positive O. Really wants those electrons back badly. So what can happen here now is that this thing is kind of souped up. Its reactivity is souped up compared to where we started. You've added a proton to make this thing more reactive, and then the nucleophile can attack. And you will find that the nucleophile does not have to be a strong nucleophile. It's very much like an SN1 reaction. You have put this nucleophile, even if it's weak, in the presence of something highly reactive. This is not a carbocation per se, but it's very much like one. You've protonated this oxygen to make that thing more reactive. Now, at the end of the day, we have the attack of the nucleophile onto this thing in the second step, and we end up with the same product. So if you're going to spend any time on this material soon, it needs to be this slide. This is key to what will come next. Anybody got any questions? Michael? Oh yes, yes. Resonance will be important here. Not so much to be pedantic, but to understand why things are happening. Yeah, why is it okay to do a certain step? Because you'll be making decisions in the near future. Is this step reversible or not? And guess what? I'm going to test you stuff that you haven't seen. I'm going to try and ask you to project. What have you learned, and what can you take with you? And it will be a system that might be a resonance-based system. So you need to know resonance. So let's get going. This adds a little bit of sort of flesh to what I just said. We will do a lot of reactions which are catalyzed. Catalysis now gets important. Obviously, it's important in biochemistry. So catalysis, what do you do to make a reaction faster? You often add a catalyst. And a catalyst serves two purposes, right? What does the catalyst do? Lowers the activation barrier. So in English, what does that mean? Makes it go faster. Yeah? Lowers the reaction barrier, makes it go faster. But what's the important criterion for a catalyst at the end of the day? You've got to get it back. You have to recycle it and get it back. Exactly. You have to recycle it and get it back so it can go back and react again. So we're going to see a lot of acid catalysis, we're going to see a lot of base catalysis. Important stuff, and I think for most people, interesting stuff. So here we go. This is a good electrophile. On the left-hand side, this ketone is without doubt a good electrophile because the carbon is delta positive. You put a methyl group in there, like methyl magnesium bromide, you'll get a reaction like that. Yeah? Have you done the Grignard yet? You're doing it. You're about to do it. You're doing it. Be very careful when you do it, all right? Because you might end up doing this 3 or 4 times. Make sure everything's dry. If you put a Grignard in the presence of that ketone, away we go. Chemistry. Because the Grignard's so reactive, the ketone has no chance. It's done, okay? But what if you can't use a Grignard? What if we're not trying to use a Grignard? Well, maybe we can enhance the reactivity of this system by adding a proton to produce this species. And as Michael says, resonance structures are important here. This idea that this molecule on the top right is somewhere in between those two structures. But certainly it looks a lot like this. And what does that remind you of? Carbocation. It looks like an SN1 process. And what do carbocations need most of all? Electrons. So there'll be something around here like water or an amine or a sulfur with a lone pair that can then help out after the fact because this carbocation now is so reactive. So that's key. You are making these things more reactive by either protonating and later deprotonating. This is important down here. We have not said a lot yet about equilibrium. We need to understand the possibilities now of when we go to the other side, can we come back? We did a bit of this when we did the 1, 2, and 1, 4 stuff. Those ideas of kinetic and thermodynamic control. A lot of that stuff now will be, we'll build on that. So we can take something like HCl. Let's say you're putting this in the presence of HCl. It turns out if you add HCl to a carbonyl like a ketone, you can get protonation of the O and the chlorine can attack. And you can produce this stuff on the right-hand side. But the reality is the equilibrium here favors the left-hand side. This is subtle. So what do you know about chloride as a nucleophile? Great, okay. It's okay, yeah. It's one of those decent ones. It's okay as a nucleophile. What do you know about it as a leaving group? Oh yeah, yeah, pretty good. So the pathway to go forwards in any equilibrium system needs to be identical to the reverse process. So in this case, we're protonating, and then the chloride's coming in. Protonate, chloride comes in. The opposite example has to be chloride come off and then proton come off. So what will happen here is this will break off. We'll form a plus charge right there, and then we'll take off that proton. That mechanism will be key for much of what's to come. The equilibrium here suggests that this side is favored, and that carbonyl is not bad. It's worth about 170 kcals per mole. You'll see that number in the near future. And chlorine's a good leaving group. Plus, how big is chlorine? It's large, right? So you're now putting an atom on a carbon which is sp3 hybridized, and maybe that chlorine's starting to cause some compression problems, and maybe it doesn't want to be attached there. That system to us is useless. We don't use that system at all. But it does exemplify where we go in the near future. Asking the question, can I go backwards? And if I can go backwards, which side is favored, left or right? We did this a bit, didn't we, a while back, acids and bases? So if you remember that stuff, you're in good shape. Here we go. This is your next 2 weeks. You have nothing else to do with your lives. It's going to snow again. Just get on this stuff. We are going to spend time talking about oxygen nucleophiles. Water being a very simple example. Alcohols being a very useful example. And these diols being a particularly useful example. We'll then start about sulfur. Sulfur is the sulfuric, or these thiols are the equivalent of the sulfur equivalent of the alcohols. So you'll find that the mechanisms for these two are very similar to the mechanisms for these over here. You won't have to learn them twice. Then we'll talk about amines. And amines are incredibly important. I just mentioned at the beginning of class the idea of biochemistry and amino acids. and the need to take out nitrogen or put nitrogen into molecules, well, we need to know some amine chemistry to be able to do that. These will be a bit different. The chemistry of these things over here is a little bit different to the stuff on the right. But it's all fundamentally the same. Maybe you'll protonate something, then attack it with one of these species. We did this. Make a note, you already know that chemistry. Hydrides attacking aldehydes and ketones, we are done with. You make alcohols of the product. We have done the Grignards. We'll use them. You can imagine now where a 37-step homework problem comes from on the problem sets, just adding all this stuff together. We have done this stuff. We haven't done this, but it's very similar. And we certainly haven't done this, which is everybody's favorite, the Wittig reaction. And we'll get to that probably in about a week. So again, what's the common thing here? They're all nucleophiles. What do you need to be a nucleophile? What's the basic requirement to be a nucleophile? What do you absolutely have to have on an atom to be a nucleophile? A lone pair. So every single one of these atoms has a lone pair. Make a note of that. No lone pair, no nucleophile. So to get started, we will talk about hydrates. And hydrates are a bit of a nuisance. They're incredibly important in oxidation chemistry. At the end of this, we'll be able to give every single detail of those oxidation reactions we did last 6 weeks ago, where we oxidized with chromic acid and it didn't stop the aldehyde. Why didn't it stop the aldehyde? Because you get hydrates. And these hydrates now are not so much useful in terms of their synthetic chemistry, but we have to be aware that they are there. If you were doing NMR spectroscopy of an aldehyde in very humid conditions, the aldehyde might not show up because there's water in the tube that you're using for the sample, and it's formed a hydrate. But if you run the same sample in Arizona where it's very dry, you'll see the aldehyde. So we need to be aware that these things are there. So here we go, some facts. If you take acetone, which you've done this experiment yourselves, assuming you wash your dishes in the lab. You take acetone and you mix it with water, they can react. The water has lone pairs. We can go after the carbonyl, we can push up electrons onto the O, we can get a proton onto the other oxygen, and we make a hydrate. A hydrate is a functional group that you have seen, but we haven't explained it in great detail. Well, things to be aware of. sp2 hybrid on the left. The two R groups are far away from each other. sp3 on the right, the two R groups are getting closer to each other. That might be a problem. Also on the left, alkyl groups are stabilizing the carbonyl, and you don't have that concern on the right, because the carbonyl is gone. What we need to worry about here is this. And the experiments below give you an idea of how subtle the differences are between aldehydes and ketones. If you take acetone in the lab, and you take a bottle of that stuff and take an NMR spectrum along the corridor, you will see the alkyl groups alpha the carbonyl. You will see the signals at 2.1 ppm, sharp singlet with 6 hydrogens if you like, because it's all acetone. In other words, the water isn't that interested in the acetone. And you can measure that. It's 99% of this, the left-hand side is favored. Now you change that experiment. You take a little bit of formaldehyde, which is the aldehyde version. Take out the alkyl groups, put a hydrogen in there instead, and you put some water in there and take its NMR spectrum. You won't see the signals at 9. The signals at 9 are gone because it's no longer an aldehyde. The aldehyde got hydrated. And now it's flipped completely. You've gone from a system in which the left-hand side was pretty much completely favored to a system in which the right-hand side is pretty much completely favored. Obviously, we have to wonder about why. So to think about these things, we have to be concerned with stability. And again, if any of you are taking biochem, this needs to be interesting. This needs to be something that you like, or else biochem becomes something that you hate. And anybody who wants to be a physician, pharmacist, graduate student, this is key. Staying awake in things that you're not so keen on. Here are some experiments. If you take formaldehyde, as we just did, and you add water to it, it completely converts to the hydrate on the right. That's a fact. In this case, on the other slide, we said 99.9%. On this slide, we go back and say K is huge. The equilibrium constant is very much favored to the right-hand side. If you do the same experiment with acetaldehyde, which has one alkyl group and one hydrogen, you get approximately 50-50 with both. In other words, the right-hand side gets formed and some of it comes back and you get the equilibrium where you have an equal amount of this and an equal amount of this. And you can measure that by spectroscopy quite easily. At the bottom, the ketone, the acetone, where we've now swapped out both hydrogens for alkyl groups, we now have the opposite. In this case, K is very, very small. In other words, the left-hand side is heavily favored. So the ideas now are to do with electronic stability versus steric environment. Because any equilibrium, the outcome in terms of how much of each side that you have is based on their relative stabilities. If the right-hand side is heavily favored, the right-hand side is way more stable. You should have got that from the acid-base chemistry a while back. If the left-hand side is heavily favored, the left-hand side is way more stable than the right-hand side. So let's put this into practice. On the left-hand side, the aldehyde at the top, we don't have any alkyl groups stabilizing it. And that ties in with what we said earlier. Aldehydes are more reactive than ketones. They're less stable than ketones. So if I bring a molecule of water in here to form a new single bond, and I get rid of a pi bond, is that typically a good thing or a bad thing? Swapping a pi bond for a single bond. It's a good thing. Yeah, single bonds are stronger. So if I do that, Brock, you've missed it, man. I just explained medical school to you. Damn. The molecule at the top left is reactive because it's an aldehyde, and we have a nucleophile in here, water, and we're attacking this and we're producing the species on the right by nucleophilic addition. But this species on the right is pretty good. We swapped a pi bond for a single bond. That's thermodynamically favorable. And we only have hydrogens attached. Hydrogens are not going to get in each other's way. You can put them quite close, they're not going to interact. You put methyl groups there, they're going to see each other. So the idea now is that this molecule on the top right isn't bad. No steric compression, because we just have hydrogens there, and we have a single bond versus a pi bond. Great. That's why the right-hand side is favored. Now move down to the middle one. Take off one of those hydrogens, replace it with a methyl group. What do you know about a methyl group versus a hydrogen? Give me some properties of a methyl versus a hydrogen. It's larger, it's bigger, certainly. What about its electronic characteristics? What can a methyl group do that a hydrogen really can't do? Push electrons in, electron donating. So that would suggest that this alkyl group here should stabilize the aldehyde versus the one above it. And then when you go to the right-hand side, that methyl group is bigger. It's starting to see the other atoms around that sp3 carbon. So does that methyl group stabilize this product or destabilize it? Destabilize it a little bit. To the extent that between those two factors, we now have an equilibrium constant of about 1. Right-hand side and left-hand side are about the same. Go to the other extreme. What's so good about the ketone? What's so good about having two alkyl groups on that carbonyl? Stabilized by pushing electrons towards the carbonyl, by the alkyl groups. And on the right-hand side now, those two alkyl groups are getting quite close to each other. And you get compression. And so that destabilizes the right-hand side, and the molecule, the system prefers to be on the left. That is important. That really has to be understood. Now, what can get worse here? How can you make this system worse? What could you put on here to make it even worse? T-butyls. If in doubt, hit it with a T-butyl. It won't get back up. Yeah? You can guess that the equilibrium constant for that T-butyl system is probably incredibly low that you can't measure it. So now we can start to play games. Pierce, you alluded to this earlier. What can you change on this methyl group to make it less stabilized? If a methyl group pushes electrons in, what can you add to that methyl group or replace in that methyl group, with, to make this system less stable, even though it's a ketone? Oh, Samuel hits it. It's an electron withdrawing group. Put an electron withdrawing group on there. And something simple like CF3, CBr3, things like that. They will change things completely. Yes, they're alkyl groups, and yes, they're ketones, but they're destabilizing because they're electron withdrawing groups. If you got this with benzene, this isn't bad. So here are our mechanisms. I've got 5 minutes. I've got 10 minutes. I'm going to start this now, and you're going to spend some time looking at it, and then we're going to think about, on Friday, the use of these things as protecting groups. So I said earlier on, we will have 2 different pathways. Many of these reactions will be acid catalyzed. Many of them will be base catalyzed. Some of them can be both. The formation of a hydrate can be both. We can add a proton and protonate something and then attack, or we can add a nucleophile and then afterwards protonate it. So at the top, very quickly at the top, what's the pH? Greater than 7 or less than 7? Greater than 7. How much acid do I have around? Not an awful lot. No H+. I do have an acid, because water's amphoteric, it can behave as an acid, right? but it's certainly not going to behave purely as H+. It'll behave as H delta plus. What's happening at the top is the attack on an aldehyde of hydroxide. The hydroxide was added to the flask as a nucleophile / base to make the pH greater than 7 and to allow for attack. So I have a pretty good nucleophile, hydroxide. It's going after the aldehyde in a nucleophilic addition from 107 degrees. Transition state involves buildup of charge on the oxygen and loss of charge from this one from the hydroxyl. You're heading towards an sp3 product. And that results in the formation of this. And this alkoxide has to be negative because you're at high pH. This then needs a proton. If you've run this reaction in water, which is an obvious thing to do, to dissolve the hydroxide up, you have a proton source. And that proton then can get picked off by the alkoxide, and you end up with this over here. That is completely analogous to something we studied right at the beginning of term. That is pretty much the same type of reaction as the sodium borohydride reduction, where we're allowed to use sodium borohydride in methanol, in water, because it was not super basic, it didn't deprotonate the solvent, but at the end of the reaction you had the proton source, you had the solvent around, without having to add a second acid. Put that next to the sodium borohydride, it's exactly the same. So nucleophilic addition in the first step, pushing electrons onto the oxygen, and then secondly an acid-base reaction to give that product. Why not do an acid-base reaction first? Why not just protonate this carbonyl? Let's see who's been awake. Why not just simply protonate that carbonyl at the beginning and get it over with? Because there isn't any acid, because you're at high pH. Yeah, and these are things, you know, I'll grade a 200-point final at the end of this, and I'll look at the 200-point final, and I might have somebody who's on like 59.99999% in my class. And to get a pass, you need a 60, right? And if that person doesn't understand pH, there's no way I'm letting them pass my class. Because you can't do biochem, you can't do what else comes next. So make sure you understand pH. If you don't need to take biochem, same criteria. For those of you who are trying to hedge your bets, right? No. You need to understand pH. There's the basic reaction. And I guarantee at the end of the next week, you'll put all these reactions together, you'll be able to put them together on 2 pages. Basic conditions over here, acidic conditions over here. They'll have lots in common. This side will be the same, this will be different, but all the reactions will be related. Now let's do this at the bottom. What is the pH here? Less than 7. How do you make a pH less than 7? What do you add? Add acid, I think so. You add some acid from the bottle of acid. You put it in there. You add the proton source. At the top you didn't. You added the hydroxide, no acid. At the bottom you do have acid. So now, fastest reaction we know about is acid-base chemistry. We have that acid available to do this. So let's go after this lone pair. In this system, it's fairly simple because there's only one site where lone pairs are. Later on, we'll have 4, 5, 6 of them. You have to decide which one's best. That lone pair goes after that H. This water breaks off. That's an acid-base reaction. You could also call it an SN2 reaction. They're the same thing. And you produce this, and this is our protonated carbonyl. This thing is now souped up. It's now, you know, ready to go. It's more reactive, more electrophilic than where we were to start with. The carbon now is very positive, and the oxygen wants its lone pair back. So what can happen now is even a weak nucleophile like water can come in, and it can go after that carbon and produce this product. You'll be seeing a lot of these things in the next few weeks. I think I've stated several times that if you're under acidic conditions, everything along the reaction profile should be positive. So here, positive, here, positive, here, positive, and this breaks off as H3O plus. Everything's positive. It fits, it works. And it needs to make sense why. This is good because I'm bringing in a nucleophile, I'm attacking the carbonyl, and I'm making a single bond, no problems with compression because it's an aldehyde, and I make this. But this isn't quite the product. This is the conjugate acid of the product. You then have to lose a proton, typically to the solvent. Don't forget solvents there present in excess. There's lots of it. You can use more of those molecules to be able to do this again, and you can end up again with a hydrate. So the key here is you end up in the same place, but through quite different pathways. Anybody want to say anything? Kyle, you look happy with this. Is this right? Yeah, good man. Maybe we'll convert you into a chemist. What's your major? Chemistry. Oh, forget that. There's no money in that. No. Anybody? If you see any of the TAs this week, congratulate them because they all got into PhD school. Cephas and Philemon and who else was looking this year? Mike, you don't know Mike, and Jen, who was SI leader last year, also got in, so they're all off the PhD programs. Now, the last thing I'll say today is this idea of generality. This section and what's to happen next as a platform for biochem is as difficult as you want to make it individually. If you know nothing coming into this, this isn't going to be any fun. If you have kept up with this stuff in your sort of, BC type range, you should be okay as long as you put the time in. I know there are people who habitually don't come to class, and that's not my problem. They should be here. But if you're here, you should be seeing patterns. And you should be seeing things that are allowing you to learn this stuff logically without spending more time than you have to. So when I come back on Friday and I talk about this idea of what's called an acetal, the mechanism for formation of these things will be exactly the same as this, except I will replace this with maybe a CH3, and I'll replace this with a CH3. The mechanism will be the same. And the beauty of acetals is that they're very important in biochemistry as carbohydrate linkers. If you're chewing gum or you're about to eat something, you're going to be doing acetal chemistry all over because that's how you break down carbohydrates. So acetals are related to hydrates. There's a hydrate, 2 hydroxyls. There's an acetal, 2 OR groups. And those now give us some very useful properties to be able to block carbonyls. So have a look at this stuff for Friday. And again, I go as fast as you let me and keep up.